Hello and welcome back to another session on data mining. We know that machine learning can be broadly divided into, or machine learning methods can be broadly divided into two categories, those being supervised and unsupervised methods. The supervised methods typically they take in the features or an input example and its associated label. So there's a supervisory signal available directly for us to be able to optimize the parameters of the machine learning model for classification or for regression that we want. And the goal is essentially to learn a function or a mapping from X to Y. That's what we do in supervised learning and unsupervised learning. We are just given the data, no supervisory signal on what labels should be associated with it. And what we want to do is to learn some underlying hidden structure of the data. And we've talked about clustering, we talked about k-means, we've also talked about dimensionality reduction methods, and those are all examples of these unsupervised learning methods. Now, what we're going to talk about next is something called autoencoders, which is essentially a way or an unsupervised way of learning uh, meaningful representations of your given statistics. Now, we've already covered principal component analysis. So if you're clear about that, that is, there are correlations between different features of a given example, and you can exploit that to reduce the number of examples or the number of features, sorry, that you have for a given example, and you can use that as a code vector for further classification. That's going to prove really useful. Okay, because these autoencoders essentially do the same thing. Let's say you have an image. Let's say it's a 28 by 28 image, and you want to learn a reduced featured vector representation of it. So the input feature representation is, let's say, 28 by 28 or 784 dimensional. And what we want to do is we want to learn a reduced representation or lower dimensional representation of this. And we can do that using autoencoders, which are specialized types of neural networks, which have a sort of a hourglass or a bottleneck structure. What these do is that they pass your input to the neural network through a neural network, which generates a set of features for a given example that we've called Z. And those features are then passed on to another part of the neural network, which then regenerates or reconstructs your input example X that you had given as input based only on the feature representation Z that it has learned. Okay, so the loss function for this particular case is the reconstruction loss, much like what we talked about in principal component analysis. You have your X, which is your input for a given example, and you have a reconstructed input from X. So you can probably divide it into two bits. One of them is the encoder block or the encoder network, and the other part is a decoder network. You can pass your input example X through a bunch of neural network layers, which allows you to reduce the feature dimensionality of your network, of your given data. So the first bit of this encoder block, what it does is that it takes your X as input. It has a certain set of parameters or weights that I'm going to call theta E for encoder, and it generates, for a given example, your an output Z. Okay, and what happens with this Z is then that goes into the decoder block, and the decoder has a bunch of parameters of its own. So it's a neural network that I'm calling D, and it takes that feature representation or code, as it is called, as input, and then generates a reconstructed version of this X. So the optimization problem then becomes that we want to minimize the error between X and X prime or X hat. So we want to learn such parameters or such values of theta E and theta D so that this error is minimized, not only for this particular example, but typically for a bunch of examples. So I is equal to 1 to n, and you have this. So this is how these autoencoders work. The goal is to learn a reduced representation for a given input image. So let's say you have a neural network that we call the encoder network that maps a given example, which is let's say in d dimensions. So this is how you denote in mathematics or in machine learning lingo that this example is d-dimensional because it's a vector that has real numbers, and those are there d different numbers there. So we pass that through an encoder block, and we get a z vector, which is a vector in d prime or d hat dimensions, and then we can use that to reconstruct this uh, generate a reconstruction which is also in this d-dimensional space. So you can think of PCA. If you think of PCA, it's a single layer autoencoder. You have a single layer of vectors. It reduces the number of features. If you have d features, you get d dash features by doing a dot product with a weight vector w or weight matrix w that can be learned directly by explicitly minimizing this or solving this optimization problem. So here we can do nonlinear nonlinear dimensionality reduction by having the first part, the encoder block, instead of having just a weight matrix, you can have a whole neural network there. And that's going to be really useful. So what these allow us to do essentially is to model the structure of data in a given example. So this is how you can train a neural network. So an autoencoder is essentially an unsupervised approach for learning lower dimensional feature representations from unlabeled data in the training set. So you have an input image, you pass it through a neural network encoder, you generate a code which is typically less than 784 dimensional, or the number of input dimensions you have. You pass it through the neural network decoder, which generates a reconstruction image. And what we want to do is we want to minimize the error between the reconstruction and the original target, and we can use this dimensionality reduction to capture meaningful factors or variations in the data. And this is how you can, so this auto-encoding step, so we want to get those features that essentially auto-encode or encode us given examples that allow reconstruction. So you have a neural network, so you have an input image, we call it X. We pass it through a layer of neural networks, neural network layer that I indicate with this weight matrix W. So let's say your input representation is 784 dimensional over here, and this weight matrix has, so it's going to have, let's say we can have 20 different features at the output, and each of them is going to have 784 rows. So when you take a dot product of this W and X, you are going to end up with a code vector which is now lower dimensional in comparison to your input. And what you want to do is you can use either the transpose of the same matrix to generate or to reconstruct the same image. So remember, if you have an input example that is 784 dimensional and you multiply it with a weight vector that, or a weight matrix that is 20 by 784, if you do that, what you're gonna end up with is, sorry, I should have used it the other way around, 784 by 20, okay? And if you multiply that, you are gonna end up with a 20-dimensional vector representation, which is going to form your code, and then you can go back to your reconstruction of your input example by multiplying with the weight, with the transpose of the same weight matrix. So this is called a symmetric autoencoder because you have used essentially the same matrix in both the encoding and the decoding blocks. That is not a requirement. You can essentially use an encoder matrix and you can use a decoder matrix, which can be completely different from each other. Okay, so you get a lower dimensional representation and you can minimize that error, and that's how this weight matrix is learned. Okay, so you got an input layer and then you got a hidden layer that is called also a bottleneck layer. This should be layer, and you can have an encode and decode section. Okay, so the output of the hidden layer is the code. So let's say if you want to send a message that is really big and you want to send it over the network, which is slow, you may want to compress that representation using an autoencoder so that a part of that encoder stays with you. What you do is you pass your message into the neural network, you generate a lower dimensional representation, you send that representation over the network to the other side, and they have the decoder block now. And what they can do now is use that decoder block to get an estimation or a reconstruction of your data that you wanted to send. And of course, these can be deep as well. You can have multiple layers. You can have multiple convolutional blocks in there. So let's say your input image is given over here. You pass it through multiple layers. Each of those layers can have a convolutional block as well. They can have a fully connected block in there as well. And you end up with a decoder section that allows you to reconstruct. So there's an encoder. This bit gives you the code, and then the other bit gives you the corresponding output. And this is how you can use these autoencoders in order to generate, in order to encode your or reduce the feature dimensionality of your data using neural networks.